Hello, everyone. Welcome to Train of Thought's presentation on our Capstone, focused on the automatic inspection system for railroads. My team members include Cassidy Anderson, Jake Hinkle, myself, Ethan Keck, Trevor Krautler, Zach Wensler, and Adam Zarashak, and our advisor is Dr. Jacqueline Novel. So, train derailments can cause millions of dollars of damage, as well as the loss of life. We in the JMU community are also not far from the effects of train derailments, as just as recently as May of 2017, a 5-car corn grain train traveling through downtown Harrisonburg derailed, spilling contents and cutting out power to parts of campus. We, however, cannot focus on only our local community if we want to be able to prevent a derailment, such as was written in our Capstone contract. Throughout all mainline railroads in the US carrying goods and passengers, 44.9% of derailments can be attributed to track failures, as you can see in this diagram shown on the slide, while 22.9% of recent derailments are attributed to more specifically surface level defects. These defects can be cracks in the surface of the rail, pictured on the left, circled by the red circle, and in this particular case, it is a weld crack where 2 rails were bonded and the weld failed, as well as rail burns, which is shown on the right, which is where rails are actually flattened on the surface due to high friction occurring between a wheel and a wheel of a train and the rail it is making contact with. A fundamental part of a surface level defect is that rails will wear with time, and many of the rails in the US are upwards 60, 70 years old and still operating on modern tracks. The more wear a rail receives, the more likely it is to fail. There can be cracks and burns and other defects that will be exponentialized, leading to higher chances of derailment. In order to keep up with these surface level defects, rail inspectors and operating companies must consistently check and maintain miles and miles of rail at a time to meet Federal Rail Administration safety requirements. Companies that we identified as good examples for different levels of requirements would be the Shenandoah Valley Railroad, with 20 miles of rail here in the Harrisonburg Valley, as well as Norfolk Southern and their 21.5 thousand miles of rail. Shenandoah Valley Railroad will most likely be using manual inspection based on what their inspectors let us know, while Norfolk Southern will use multi-system train car-based inspection systems, such as the one pictured here as the orange Sperry vehicle. Sperry is an internationally known inspection system company, and they contract out inspection vehicles to large-scale railroads to detect all sorts of surface-level defects as well as geometry. Now, inspection vehicles are very costly to contract and are often out of the budget range of many of the railroads that we look at. For example, Buckingham Railroad Branch Railroad is highlighted here on this map of Virginia. The railroad services enough rails to require more than just manual inspection alone, but does not move enough value across its ecosystem to support the cost of an inspection system such as Sperry due to the high costs and the operating costs of hiring someone that can use the vehicle. We as a team have planned to create a system to inspect rails for surface level defects that can operate with manual inspectors to allow them to cover more rail while staying within FRA regulations. The reason we came to this conclusion was the idea that regulations permit that inspectors can only inspect 2 rails at a time if those rails are close enough to each other, while also maintaining a slow speed if unassisted. This slow speed is due to them using manual inspection equipment that is physically placed on the rail at certain sections that they identify as needing to be checked. FRA regulation also permits inspection vehicles to be sent out ahead of manual inspectors to give early warnings to high rail vehicles, such as the pickup trucks that you may see driving by on your local railroads, inspecting vehicles and carrying inspectors in them. Our initial prototype was the use of a 2-rail system shown simply in the CAD model above that would take live feed of the rails with a video camera, push still images into a program that would then identify it as good or bad rail. The program we developed would be machine learning on MATLAB. We took images of a mock rail pictured on the slide as a pink foam board and would identify these images as good or bad rail for the machine learning library. As we taught the machine learning, it would then be able to identify future similarly looking images on its own without the help of a moderator. This, however, takes much time and will be needed to be improved in the future. After creating this mock inspection system, we needed to plan the integration of structure, software, power, and electronics. We CAD modeled a few basic frames, as well as looked into traction batteries, which are similar to those found in vehicles such as EVs, electric golf carts, as well as forklifts. Our plan is to put a physical model together and test it on the rails we received as donation and loan from Shenandoah Valley Railroad in the spring, where we will then make adjustments to the placement of cameras, propulsion, electronics to be tested in the fall. The team will also inquire about making the inspection system modular, as we are interested in not only having video feed, but also a 3D laser scanning system. 3D scanning would allow the team to more accurately determine the severity of defects detected, allowing manual inspectors to rapidly determine future steps that they need to take in order to correct the damage that they have found. This would also help us, as having a camera feed would allow them to have a basic view that they would then be able to take a closer look at, or they could modularly switch out the 3D scanner if they want to be more in depth with their scan of a certain track that they have to inspect multiple times in a month, such as once a week. Before we can do that, we as a team invite you to watch our video on our team blog, where we go into more depth on the machine learning process that we have underwent and discuss the adjustments our team has made following remote learning. We also challenge by choice anyone to fill out our support form on our blog, where you can give us insightful information or learn more about our capstone. I want to thank everyone for your time, and I want to thank all the other panelists for being here at our xChange. And I would welcome you all to come check out our blog and give us some insight. Please, any questions now?